Today we're going to talk about related rates. In many equations, when one aspect of the equation changes, another aspect will change as a result. We can say the two aspects are related. For example, let's look at a circle. If I take a circle and I increase the radius, the area of that circle increases as well. The formula is area equals pi r squared. This equation shows the relationship. This is a direct relationship. As the radius increases, the area will increase as well. It's going to increase quickly because radius is squared in the equation. The second part of related rates will be the rate. When some quantity is changed with respect to time, we call it a rate of change. Acceleration is the rate of change in velocity. The rate tells us that we're changing the velocity with respect to time. We write it as acceleration is the change in velocity over time. In calculus, related rates are used to determine how quickly a quantity changes when another quantity is changing. Let's recall. The slope of a function is the change in y values compared to the change in x values. We write it, the change in y values compared to the change in x values. In other words, the change in y with respect to x. We also know from earlier calculus that the slope of a function is equal to the derivative of that function. That can also be written dy dx. To solve related rate problems, we will need to find the derivative of an equation with respect to time. This will most likely involve implicit differentiation. For example, if the radius of a circle increases at a rate of 2 centimeters per second, find how fast the area of the circle is changing at the instant in time when the radius is 5 centimeters. In other words, we want to find the rate of change in the area of the circle. Let's start with a sketch. There's our circle. What do we know? Well, we're told the rate of change for the radius. So we're told the rate of change we will write as dr over dt. The r is radius and it's over time. So the rate of change of the radius is 2 centimeters per second. We're also told at the instant in time when the radius is 5 centimeters. So we know at this instant in time the radius is 5 centimeters. We should also write down what we want to find. We want to find how fast the area of the circle is changing, or the rate of change in area. It's a rate, so we put it over time. This is what we want to find. Then let's choose the equation that we're going to work with. Between area and radius of a circle, our equation is A equals pi r squared. I'm going to take the derivative of this equation with respect to time. That's where our implicit differentiation is going to occur. The derivative of A would be 1, but it's not a time, so we write dA dt. The derivative of A with respect to time. The derivative of r now with respect to time is going to follow the power rule. I'm going to move the 2 down in front. Subtract 1 from the power. So I have 2 pi r, but once again, it's not a time measurement, so we have to add in dr dt. That is the first derivative. Now we can substitute and solve. 2 pi r is 5 centimeters. dr dt is 2 centimeters per second squared. Or centimeters per second, sorry. If we put all of this together, the rate of change of area will be 20 pi. Putting in our units, we'll have centimeters squared per second. In another video, we'll go through a second example.